There's so many people. There's so many people.
Dus een verdeling is streng. Het is een convention to make a point only point this way, point that way, which is a convention how we cope with So whatever is observable, these spreads much more to the sides. See the pictures code, this is code and what is key of how we label it.
Okay, before we get started with this afternoon's talk, a little short announcement. Tonight we have the last of the dinners, and so at 6:30ish we'll go to the other building to where the cafeteria is, and outside in the hallway there we will have a buffet. And so there will be drinks and food there from 6:30ish onwards. So that's for tonight. First we'll have Mehdi Kargarian, who will talk about topological quantum computations. And this is actually, I think, the first applications type talk in using non-median statistics, so we're very happy that you will.
Thanks.
About that.
Okay, I want to tell you about the topological quantum computation models and the two-edged Hamiltonians. First, I would like to emphasize that this talk is not directly related to the quantum physics and will not come from the main subject of the workshop. But the point is that even in the quantum physics, the loveliness states are not the exact wave function of a two-edged Hamiltonian. And however, they capture the main physics of two-edged Hamiltonians. And in this talk, I will invoke the decimal lattice models that are important for the topological quantum computation model and provide a platform for a topological quantum computation. But the point is that in this quantum lattice model, such as the Turicode model and about the Turicode model, you also hear from the trivial talks at the early days of the workshop. The main point about this lattice model is that the underlying Hamiltonian is a many-body Hamiltonian. That means each term of the Hamiltonian is just a product of the many Pauli operator, and it is very demanding from the experimental and from practical point of view to detect in the nature of alternatively in the optical lattices. And now the question arises: how we can adopt a topological quantum computation model for example, the Turicode model or the Collier model that I will talk about there, as a grounded state of or at least as grounded state, or at least an approximate grounded state of a two-edged. Okay, I would like to thank my collaborators, Victor Bombi and Miguel Martin Delgado. Okay, to this end, first I will briefly review the quantum error function codes based on the topological stabilizer codes. And then I will talk about the Turicode model. And then the main subject of my talk will focus on the color code model. That is another whole class of topological stabilizer codes with the enhanced computational capabilities as we compare to the Turicode model. Then I will introduce a two-way lattice Hamiltonian that gives the color code model as one of its phases. And then I will study this two-way lattice Hamiltonian by means of fermionic mapping and bosonic mappings. And finally, I will in the case of classical computers, which work based on the bits, there is a very complex error correction recovery process based on the classical error correction code. This code works based on the repetition codes. But and the two important properties of such error correction, of such successful error correction, is that the only error that can occur in a classical state are of bit flipping error, and most importantly, we can observe the state and observe the error and then correct it. But in the quantum computer that works based on the estates of the many qubits, and the process is not trivial, because in the quantum case, in addition to the bit flipping error, the phase flipping error and other errors such as rotation can accumulate with the system and destroy the information. And perhaps most importantly, the decoherence in the bit of staking and physical realization of the model. However, the decoherence is not so bad, because we are here because of the decoherence. Okay. We cannot generalize the error recovery process from the classical state to the quantum state, because we cannot copy the quantum state because of the nuclear theory. And most importantly, we cannot observe the state, because any effort for observing the state erased with the coherence and the destroy of the quantum information. Despite of these difficulties, the error correction, quantum error correction is possible. Which was pioneered by the short construct code, in which we can, in which the quantum information can spread over several qubits, and the bit Philip error and the phase Philip error can be corrected. In fact, in the short code, we can measure the errors, not the state. And this was the important property of the short code. Essentially, coding a space that we use to code the quantum information is just a subspace of the Hilbert space that is by several states. And the code is quantum error correction code if and only if for any two arbitrary error syndrome we cannot distinguish between we should distinguish the state from each other after the error has occurred in the system. The main importance of this relation is that the right-hand side would not depend on the side index. Otherwise, we will get some information about the state, and this gives rise to a destroying of the information. And also, the state must be distinguished. The error must be distinguishable after the error of the states. This is the basis of the quantum error correction. Okay, the coding space can be constructed based on the stabilizer formulas. In fact, the coding space in the Hilbert space can be regarded as a fixed point with a minus, with a plus one ion value of some stabilizer operator that is a commuting subgroup of the Pauli group. And in this case, the error are just any violation of is condition. Also, there are also some errors, some operators that are not in the stabilizer group. They commute with the stabilizer group, but don't belong to the stabilizer group. These are just a non-detectable error and essential for the to construct the basis for the encoded qubits. But the main disadvantage of this error recovery is the error rate must be below than a threshold value, above which we are not able to detect the error and correct it. Okay. Now the question is that how can really how can we really get rid of decoherence and in this way one may look for a system which are increasingly robust against errors, and perhaps the topological model that which carry non-local degrees of freedom can pave the way for the so-called fault-tolerant quantum computation, because non-local degrees of freedom are very demanding to couple with the environment, and the quantum system will couple with the environment through the local interaction. So the topological model may pave the way. To make use of the topology, we put the lattice. We put the lattice model on a surface of a manifold with non-trivial topology, and the stabilizer operator are just some boundary operators that are homologous to zero. And non-detectable error, or the normalizer of the group, will stand for a non-trivial cycle of the terms. They are homologic to non-trivial cycle of the terms. The first example of such topological color code introduced by the Kidad in 1997. And the model is just a square lattice, and the qubits are located at the lengths of the lattice. With each blockade, we attach a stabilizer operator, which is just the product of the S operator and the lattice. And with each star, also we attach another stabilizer operator, which is just the product of the Z operator. The normalizer of the group are just the non-trivial loops that within the course of the torus, which form a basis for the encoded qubits. Thus, the elements of the stabilizer group are sub-boundaries. This is just the product of the blockade operators, and also the co-boundaries, which is just the product of the star operators, and the chain and the co-chain, which is defined on the direct lattice and the dual lattice, are the basis for the okay. As a curiosity, we can rotate the square lattice, in which the qubits are placed on the vertices of the two-body lattice of a bipolar lattice. In this case, the dark blockade will correspond to the previous blockade, and the white blockade will correspond to the stars. This is useful to a construction to compare it with the color code model that I will introduce later, right? And thus, a dark string, which will be the product of the white blockade, connect the dark blockades, and the same thing for the white string, right? Okay. The main important step towards the fault-tolerant quantum computation is that we should be able to perform the gates, the single qubit gate or two qubit gate transversality. Transversality means that if you consider two code layers, for example, as in this code as a control logical qubit and this as a target qubit, and if we perform the single qubit gates on all qubits, the net effect must be encoded gates. So in this way, we will not go for a selective addressing of the qubit, and this is an important step for fault-tolerant quantum computation. For example, in the surface code or the toric code model, we consider the Hadamard gate. The Hadamard gate will copy the chain forward, and according to this, and copy the co-chain backward. This is just simply the action of the C0 gate in the case of the toric code model. And to see the action of the Hadamard gate on the logical operator, we can consider a code layer which encodes a single qubit, and the top layer as a control qubit, and the bottom as the target qubit, and then and we can suppose that the X logical operators act on the top control qubit, the net action of the Hadamard, the CNOT gate will be just the encoded CNOT gate. But unfortunately, this is the only gate that we can transversally in the case of the Turing gate. We cannot perform this Hadamard gate and the phase gate in the transversal. Because, for example, the Hadamard gate preserves the code, but it get exchange the X and Z bar operators. And this means that from the practical point of view, we must rotate the lattice. And this is not so convenient from the practical point of view to rotate the lattice. Okay. The topological color code answers this question. They are defined on trivalent lattice with the links, vertices, and the blockets. We use colors as a bookkeeping tool to keep track of the vertices, links of the blockets. With each blocket, we attach two operators, which is just the product of the X operator around the blocket and the Z operator. This is different from the Turing code model. In the Turing code model, which is blocket, we attach one stabilizer operators. Okay. And then the coding space, which we call it the color code, will be fixed by the blocket operators. Also, I should emphasize that we call such a lattice a 2-collex. 2 stands for 2-dimensional, and then collex stands for collex.
All the plaquettes have to have an even number of edges? Is that, do all the plaquettes have to have?
No, we can define on any trivial lattice. However, from now on, I will consider only the hexagonal lattice for simplicity. No, general. Okay. In order to analyze the code, we can define the string operators. Color string operators is a collection of the links of that color. For example, a blue string operators is a collection of the blue links, and with each we can attach a X operator or Z operators. And the string operator with different color and type will want to commute with each other if they cross once. Okay. Also, and the other properties are that a string can be either default or branched. For example, we can get a blue string and split it into a red and green string. This property is not present in the Turing code model, and it is essential. It is crucial in this model to perform the transversal implementation of the Clifford.
So what do the colors correspond to? The model you had qubits on each side, and what am I supposed to interpret the colors as? Are those 3 directions or something? X, Y. What are the colors in this picture? Are those X, Y, and Z or something?
With each blocket, right, like this, we attach 2 stabilizer operators, right? And a string operator and a blue string operators connect the blue triangles, right?
Okay, yeah.
And for example, red string operators connect the red blocket, and the product of the 2 strings may create a green string. By this I mean that we can split
But you made the comment that it also applied to other lattice. I think this kind of property would be pretty specific for this kind of lattice you have, right? Or you know, with your lattice structure, I guess. Otherwise, you would may not be able to have.
The only the only main point of this to have such construction is that that is not being trivalent. And no,
Trivalent.
trivalent is the important ingredient of this such.
Can you back up again?
Yeah.
So the boundaries of all the blue plaquettes are all green and red.
Yeah, or blue or yeah.
Right. So if I have a triangular plaquette, I'd be in trouble, right?
I have a triangle bracket.
If I had
Right. Okay.
so there's no triangles.
No.
Okay. So I think my original question is, should all the plaquettes have an even number of sides?
Not in general.
Not in general.
No.
So how am I going to do that if I have an odd number of sides? I have to. It looks like I always have around a blue plaquette. I have red, green, red, green.
Oh
red,
yeah.
green.
Oh yeah. The number of sites around the next must be the number of sites. Yeah. Well, the number of sites. Okay. As in the surface code, we can also construct the logical operator which correspond to the anterior cycles of the torus. But the important point again is that for each homologic class, we can consider two different color schemes, and they cannot differ into each other. This means that in the case of the color code model, the coding space will be bigger than the coding. And for example, in this case, for the torus, we can encode 4 logical keywords, while in the toric code we can encode 2 keywords. Okay. Let me. In this case, you may ask why we don't consider the green state. The point is that in the color code, one of the color, only two of the color are independent. Right? For example, if I consider the green string, the product one is string can be split into the other strings, and they are not all independent. Okay. Both color code Hamiltonian and the toric code, color code and the toric code can be adopted as a ground state of the ground state manifold of the many-body Hamiltonian. The many-body Hamiltonian is just a sum over or stabilizer operator, and the coding space will be just a manifold. And in this case, the error this will stand for the excitation of the quantum many-body Hamiltonian. And in the case of the toric code, the different set of placket, the dark placket and the light placket, appear with different expression for the Pauli operators. But in the case of the color code model, the colors don't enter in the writing the Hamiltonian. But it is important for describing the groundless manifold of this many-body Hamiltonian. Okay. The groundless of such many-body Hamiltonian are carry topological order because the groundless of Pauli superposition of closed string in the case of the toric code, and string net structure in the case of the color code model because of the branching point in the strings. And the degeneration will depend on the topology of the surface, and also the topological order in the toric code related to Z2 gauge group, but in the color code will be related to Z2 or Z2 gauge. That I will back to this point in the next slides. Okay, and the excitation in the toric code model can be put on the white and the dark placket, the electric and the magnetic charge. Considering the identity sector, we will have 4 topological sector for the Turing code model. In the case of the color code model, the excitation can appear at the endpoints of the blocked operator, the string operator, or at the end of a string, at the endpoint of the string, open string nets. And the excitation with different color and type will have a mutual signaling statistics. Considering all excitation with different type and different colors, we will have 9 bosons in the system. And the important point is that we will have 2 family of the fermions in this one, right? Which is just a combination of the product operators with different color and with different type. The important properties of these 2 family of fermions is that each family of fermions is closed under the fusion. For example, consider the first family. If we fuse 2 of them, the third member is created. Or alternatively, 3 fermions will fuse into the vacuum in each family of the fermions. But the fermions from different family have trivial mutual statistics.
So how do you see this? Is that community operators or?
Yeah.
How do you get these results?
Yeah, by examining the string operators, and they cross each other at one moment, they aren't completely true. That's what we do in the Turing code model to around the
Each name is similar.
Okay, but now I want to invoke the question that how we can relate the Turing code model to the ground state of the 2D lattice Hamiltonian, and the same question for the color code model. In the case of the Turing code, the Turing code model can be adapted as an approximate ground state of a 2D lattice Hamiltonian defined on the hexagonal lattice as one of its phases. Defined on the hexagonal lattice with 2D interacting terms. On this lattice, we can identify the plotted degrees of freedom, or integrals of motion, and also the extend the blocked operator into the more extended object, the string operators. And in the diagonal limit, in the strong coupling limit at the diagonal, the model can be the 2D Hamiltonian can be up on the 2D Turing code, on the Turing code model. And now the question is that can we get something similar to color code model? The answer is yes. The lattice will introduce is a composite of triangles that are connected to each other by red and green links. And the lattice is a 4-valent lattice. We adopt a 2-valent Hamiltonian. And the different columns stand for different type of the interaction. And we claim that at the strong coupling limit on triangles, the effective Hamiltonian will be just the collective Hamiltonian that we are looking for. Okay. This 2-body lattice Hamiltonian presents several properties. Among them are the model presents exact local degeneracy in all coupling limits independent of the phase we are working with. And the model also presents 3 family of the high energy fermions which are one color. They are characterized by color. And also each family of fermions coupled to a non-trivial gauge field. The model also features the anionic fermions. That means the high energy fermions are not only the high energy excitation are not only fermions but also by different color they have mature statistics. And the estimated structure of the model gives rise to the invisible charts. In order to construct the blockade operators and identify the local symmetry of the model, we design a set of pattern rules. These rules are assigned in order to attach the Pauli operators to the qubits to the string that appear in the string. If the string that we consider in the two-body color code model are composed of the Wavy line and the flattened part. If the string is crossed by the Wavy line, it contributes Z operators. Otherwise, its contribution is determined by the outgoing link X or Y. A simple example is shown here. With each blockade, by blockade I mean an inner hexagon like this, with 3 red and 3 green links, and an outer hexagon like this, and the 6 triangle in between. With each blockade, we can attach 3 string operators, like this, and this. And using the Pauli operator algebra, it is simple to show that they are not all independent. Right? And this is just the local gauge symmetry of the model. And also these target operators commute with the Hamiltonian. And they determine the underlying local gauge symmetry of the model, which is just the Z by Z. Because each target operator is called identity. And these target operators can be extended to the string structure of the model. And the key feature of this string structure is the existence of the branching point in the triangles. That will be important in our analysis of the model. These branching points are not possible, are not present in the famous Kitab model, and this is source of some new physics in this model rather than the Kitab model. Okay. We can also consider the winding loop operator. For each homology class, we can consider 3 string operators. They commute with the Hamiltonian. And they are not, again, they are not all independent. In fact, they are subject to this constraint. And the important properties of the string with different homology and different type is that they commute with the Hamiltonian, but they don't always commute with each other. This is not a perturbative result. This shows that the model carry exact topological degeneracy in all coupling limits, independent of the phase we are working. This property is not possible. Okay. The connection to the two colleagues can be discussed even at the non-perturbative results. For example, consider a blockade like this, and consider the first string operator that we attach to the blockade. We use color to determine the type of this string. For example, we consider this string as a red string, and use a convention that this fatting part, this is a red string, and this fatting part connect the blockade with the same color. Right? So we can use red color to color some inner hexagon of the lattice, and we consider the second string as a green string, and those we can color the other inner hexagon of the lattice, and the remaining inner hexagon of the lattice we can use the blue color to. Also, the sides around around an inner hexagon can have a color of that hexagon. In this way, we can color all sides and pocket of the hexagon. And the connection to the color code has been beautifully run as this figure. The connection to the two colleagues can be further exploited by considering the string nets on two colleagues and see how the fatting part, which block the fatting part connect to each other. For example, this fatting part connect two blue blockets and these two red. And we can map into the two colleagues. This part is just the color string, the blue string which corresponds to this. So the connection can be done even at the unperturbative results. Okay. At the perturbative level, we can use the degenerate perturbation theory to show that the effective color code, the many-body color code model arises as some model of perturbation theory. The first non-trivial term arises at the sixth order of the perturbation theory, which is just the product operators, and the second non-trivial term arises as the ninth order of the perturbation. This is just the putting all terms together. This is just the color code. This means that the color code arises at the strong coupling on the triangles of two additive. Okay. Unlike the Kitov model, this two-body lattice model is not exactly solvable based on the Jordan-Wigner transformation and by using the model of fermions. We can use the break wall lattice and the one-dimensional representation of the lattice in order to check the solvability of the model. We can bring all interaction, the XX interaction, the YY interaction, the ZZ interaction. We can write all of them in terms of the Myron of fermions. And the two-body Hamiltonian in terms of the Myron of fermions look like this. And the important point about this Hamiltonian is the arising of some fields. These are just the fields that in the Kitov model commute with each other because they live on the on specially separated links and they commute with each other and we can fix them independently. But in this model they do not commute with each other because on a triangle two value links. This UIJ, they live on the links of the triangle, and two neighboring links don't commute with each other, so we cannot fix them independently. And this is thus the formal and structure of the model is the main disadvantage of this model that which doesn't allow us to solve the model exactly. Okay. Also, the model is not exactly solvable, but we can study it by using some other mapping, such as the bosonic mapping. In the bosonic mapping, we try to map the original estimate degrees of freedom to some effective degrees of freedom in which the hardcore boson attached to it. And that was first introduced by the Julian Miller in 8. To this then consider the extreme case in which the jx are set to 0. In this extreme limit, the spectrum of each triangle has just 2 degenerate ground states and 6 degenerate excitation states. 2 ground states can be adapted as two states of effective spin, and the excitation on each triangle can be considered as a hardcore boson that we put on the triangle. Just we can bring all initial spin degrees of freedom into effective degrees of freedom, the effective spin degrees of freedom, and the boson that be attached to it. Right? In this way, we can define the color annihilation operator at each triangle, and also the color number operators. Through such mapping, we can also write all original spin degrees of freedom, sigma z and sigma x and y, in terms of the new degrees of freedom. Tau stands for the Pauli operators of the effective spin degrees of freedom, and the P is just a parity operator, and the R is the color switching operators. Oh, and then we can map the Hamiltonian, bring the Hamiltonian in a new language of the effective spin of degrees of freedom and the bosonic degrees of freedom. The first thing is a constant term, and the second thing is just number operators. And the third term is just interacting between, in this way, the interacting between the bosons. From now on, we will completely forget the original two-body lattice and work on the two colleagues and for effective lattice model in which the bosons live on. The terms that appear here have a physical has a graphical interpretation. For example, the theta, this is just this way bosonic hopping from one bracket to other bracket. The U-term, this way fusion process. For example, red boson and a blue boson fuse into a green boson. And R operator describe color switching operators. For example, red and green bosons exchange their colors. And the V operator describe annihilation process. Two boson are annihilated at two brackets. And most generally, we can consider a more complicated process, which includes including a fusion process, a splitting process, and hopping and annihilation. And the existence of this vertex is very important in our analysis of this group. And this shows that the bosons are not free, and but rather they interact with each other. That's okay. Following the Levin and Wien, we can examine the statistics of the hardcore boson, the color hardcore bosons. To obtain the position of two bosons, this is just the product of some hopping operators. We can bring into product of the effective spin operators, and we get a -1. And this shows that the color hardcore boson have very unique statistics related to each other. Right? In fact, we have three family of fermions that characterized by their colors, and their colors can be regarded as as an element of the Z2 gauge. And another important property is that each bracket operator and the string operator that we attach to the bracket can be regarded as a one-dimensional representation of the gauge. Right? Thus, any fermion, again, following the Levin and Wien construction, any fermion must be coupled to a gauge. Right? To this end, we consider a process in which a color fermion, for example, here red, we take it and go around the edge, which may contain several fermion and the vortices. The phase that we pick up is composed of two terms. The first term related to the one-dimensional representation of the vortexes. The vortex has been shown by spiral lines. And it's characterized by and it's dependent on the color of the high energy field. This shows that each family of fermions see a different gauge. And the second term shows that the fermions with different colors have also mutual similar statistics. They are fermion, and they are anion related to each other. Each family of fermion, each family of high energy particles are fermion, but related to each other, they are just anions. For this matter, we call them the anionic fermion. Okay. Right. There is a correlation between the high energy sector of the model and the low energy sector of the model. By this I mean that we can locally default a high energy fermion to a low energy sector of the model. This attach a topological charge from the low energy sector to the high energy fermions. And also we can examine which topological charge carried by the open state at the end of the open states. The important point of this topological sector are that the topological charge that we attach to the high energy fermions belong to the one family of the fermions that I told you before. And the topological charge that carried by the string operators belong to the second family of the fermion. Thus, the topological chart that carried by the open string operator must be invisible to the high energy fermion because they belong to the different family. The model provides the other properties of the model can be probed in other sectors. As the excitation on a triangle of the Fermi limit provides equidistance levels, it will be very useful for the perturbative continuous unit transformation. The zero particle sectors are just the color code model at the lowest order of the perturbation, that is just the sum of the bracket operators, and in the higher order it's just the multi-bracket term appear in the Hamiltonian. In the one particle sector of the Hamiltonian, the effective Hamiltonian will be just the color code Hamiltonian, and a single term is added just this way fermionic process. For example, a single fermion annihilated as and then appear at the other terms. after a complicated filtering process. Okay. At the one particle sector, in the, up to the first order, the fermion can only do a orbital motion around the placket of that order. For example, a blue quasi-particle, a blue fermion can hop around a blue placket. And this contributes with -2J in the energy factor for the high energy fermions. In the second order of the perturbation, the fermion can hop from one orbit to the another orbit, and this will contribute and will give a non-flat dispersion for the gap. And this is an approximate estimation, but it shows that at some value for J, the gap will be closed. This is a resemblance of annually condensation. But yet, in the model, there are some topological charts that are invisible to the condensed annual, because here we are dealing with the condensation of the periphery of the fermions, and yet there are other topological charts that are invisible to the condensed annual, and they are the source of the exact topological degeneracy of the model. But this is a conjecture, and I don't know really. Okay, let me conclude. The Hamiltonian that we introduced has a symmetry of the lattice. For example, the Hamiltonian has a symmetry of such lattice, not this lattice. We may introduce a more general Hamiltonian that the coupling constant that breaks the symmetry between the colors. In that case, may gap for different excitation can be closed at different values, and this may make a rich phase diagram, a more richer phase diagram for the model. And the model is not exactly solvable based on the fermion. It might be maybe other methods such as the numeric or the I don't know can help us to determine the phase diagram of the model. It contains we don't know whether it contains it can support the non-abelian annuals or not. And finally, thanks for your attention.
Questions? Do you have any indication? So you have this excitation you subtract and you get closer somewhere, but do you know by any means that there is a gap at the lower order of coupling?
Okay, this value is this is very rough value because and it's not a good approximation. If you want to get a better value, you should consider the other order of perturbation. However, it shows that the gap may be closed.
But what I was asking actually is, could there be other excitations which already closed the gap earlier? Do you have any? Could there be other gapless excitations around already in the model?
Gap excitation?
Gapless.
Oh, no, I don't know.
You don't know?
No, I don't. Because the model is not exact. No, I don't know. Gap excitation.
Have you studied what happens if you add a term that breaks time reversal?
Oh, no. The Hamiltonian has a time reversal symmetry, but I don't know whether there is whether if there are phases that may break the time reversal symmetry.
You wrote down all the hopping terms that you get much earlier. It's complicated. next, yeah, that, so you have all these hopping terms, and it's of course still a quadratic Hamiltonian. So is this is exact or this is first order you written down here?
It's not quadratic.
This is not, but you know, on the next page, they all seem to be just hopping terms.
This?
Yeah, those all look like they're quadratic, you know, the little particle from here.
No, no.
Oh, is it
Yeah. The hopping term maybe quadratic, but there are also some fusing terms
Oh,
Which
those
they-
are not, oh,
yeah.
I see, I see.
which don't let us to bring down to any quadratic form.
So you mentioned at the end there may be sort of phase with non-abelian anions. Can you?
Maybe, I don't know.
Yeah, maybe. So can you anticipate the kind of, you know, the fusion pattern, all these things from the structure of your model?
How can I?
Do you have an expectation of what kind of non-abelian anions they would be?
About no, I have not any answer question, and I don't know because the model is not exactly so. I have not any picture about the model, whether or not the model can be supported non-abelian. I have not any clear picture of this.
Can you make an argument if you knew what the low energy sector was, so you were thinking of the low energy sector, was presumably if you look at the ground state of the torus, that tells you total number of particles. I mean, is that something that's plausible that you can just figure out what the ground state is on the torus and that'll tell you?
In the case of color code model,
Yeah. I mean, the color code model, presumably that's solved. But in the more general model, can you figure out you don't have to look at the excitations to figure out if it's possible to have non-linear statistics because you can just count the degeneracy of the torus if you can do it. You only need to look at the lowest energy sector.
yeah.
And that's not solvable.
And
Try to do some bracket operated and start moving them as you go into next or something like that. It's not clear that these are all independent, I guess. I'm not sure.
the degeneracy on the torus arises from the fact that the alpha-locket operators are not independent. Okay. For example, the product of the green operators, the green locket operators. For example, of the green locket operators. Green locket operators equals, for example, the X locket operator with the red operators, and they will provide the same action in the stabilizer code. And the same thing for the Z. And this shows that the all product operators are not independent. It's the source of the development degeneracy on the closed surface. In the case of the periodic, in the case of the open boundary condition, the model, in the simplest case, we can consider a triangle which have a three-color boundary, this, for example, this is blue border, and the red border. And in this case, the degeneracy arises from a string net. That means a string with a branching point, and each part of the string can have an endpoint at that border. And this is the source of the topological degeneracy for open.
Questions or comments? If not, let's thank the committee again.
Sure, he's still trying.
I'll be right back, sorry.
No, he also had to work on one of these models, but they're different models.